So in this episode we're going to be looking at handling numbers using scientific notation and significant figures, and also the art of investigation design in science. So we're going to start with a few contextual problems around the mathematics that you may come across in nanotechnology. So the first question states that light travels a distance of 300 million meters every second. Determine the length that is 1 light year, the distance that light travels over the course of 1 year. We're also given 2 notes. Assume that there are 365.24 days in a year to 5 significant figures, and that the value of 300 million is written to 3 significant figures. We can rewrite 300 million as 3.00 times 10 to the 8 meters, which is the distance that light travels in 1 second. We want to try and work out how far it travels in a year, so we need to make sure that we're getting closer to that goal. So we can use technology to work out how far light travels in a minute. To work out how far light travels in a minute, we simply need to put in how far light travels within a second and then multiply it by 60. So in this case we put in 3.00, and to do times 10 to the power of, we use second function and then this comma button here, which is a double E button, and then we write the power, which is 8. We then multiply by 60 because there are 60 seconds in a minute, and we have just found what a light minute is. So in order to get the output in scientific notation form, you can always go to Mode and select Sci, which is the second one on the list, SCI, for scientific notation form. So now what we want to do is we want to find out how long a light hour is, because we've got a light minute. So what we do is we multiply the light minute by 60 to get to a light hour, which is the distance that light travels in an hour. So we go second function, answer, times 60, and we have a light hour. What we want to do now is work out a light day. So we take a light hour, second function, answer, and we times it by 24, because there are 24 hours in 1 day. And then lastly, we want to work out what a light year is, because we want to find out the length that is 1 light year, the distance that light travels over the course of 1 year. So we go second function, answer, and we multiply it by 365.24, because that's the number that was given in the question, is how many days there are in a year. And hence, we have found what a light year is in meters. So the distance that light travels each year in meters. And so light travels 9.47 times 10 to the 15 meters every year. And that is to 3 significant figures, like all the calculations on the board, because in the question we were told that that 300 million value was to 3SF, and we can only be as precise as our least precise measurement. So now on to another question, and getting back to the nanotechnology theme, because after all that's what this course is all about, we're looking on the small scale. So a single oxygen atom takes up 0.16 nanometers, and the width of a human hair is 100 micrometers. Determine how many oxygen atoms can fit across a human hair. So we've got a few units we need to use here, and if you haven't become familiar with the scientific prefixes, which were shown in the last video, then it's always good to have a copy of the table in front of you. A nanometer is obviously times 10 to the negative 9, a billionth of a meter, and a micrometer is times 10 to the negative 6. But we need to do a few conversions to get that into scientific notation form. So 0.16 nanometers is the same as 0.16 billionths of a meter. Very, very tiny, these little oxygen atoms. And we know that a nanometer is 1.0 times 10 to the negative 9 meters. So what we can do is we can convert that and have 0.16 nanometers equaling 1.6 times 10 to the negative 10 meters. We can then do the same for micrometers as well. And if you're unsure on how to convert them, you can always write these numbers out in full. I'll also teach you a little trick on your calculator in just a moment, which might help as well. But when we're doing micrometers, we know it's 1.6 times 10 to the negative 6. Again, it's on the table, you just need to look it up. And then we can get that 100 micrometers is 1.0 times 10 to the negative 4 meters. So, let's have a go at trying to solve this question using our calculator. Okay, so what I'll first start off by doing is showing you how to do the conversions to scientific notation form on your calculator. Make sure that your mode, as I showed earlier in the video, is set to SCI for the best results in this conversion process. And what we're going to do, we're going to type in 0.16, which is what we got for the actual width of an oxygen atom when we have it times 10 to the negative 9 to get to nanometers. And we see that when we convert this, it's going to be 1.6 times 10 to the negative 10. So we can convert it that way. We can also convert the 100 micrometers, which is 100, then we've got the e to the negative 6. And we get 1 times 10 to the negative 4. So that's a good way to double check your conversions or to actually do your conversions. But what we'll do now is we'll work on determining how many oxygen atoms actually fit across the hair. So what we need to do in order to do this is set up a quotient bar, because we're going to have the width of a human hair divided by the actual width of an oxygen atom. So in order to set up a quotient bar, you could technically use brackets in the equation, but with the quotient bar it's a lot neater. So you go to this alpha button, the green button here, and then you press the y equals button, and you get up a list. What you want to do is you want to select the first one from the list. And there we go, we have a quotient bar. It's the same as a divide bar. So what we do is we type in the width of a human hair, which is 1, and second function e, obviously the double E button there, to the negative 4. And then in the denominator, we have to do the actual width of a single oxygen atom. So we've got 1.6, second function, double E button, to the negative 10. And so what we have there is a number of oxygen atoms that can fit across a human hair. It's quite a large number actually, 6.25 times 10 to the power of 5. Now in the question it said 100 micrometers. This can be somewhat ambiguous because it could be exactly 100 micrometers or to 3 SF, or it could be 100 just written to 1 SF. So in this case, you could either write this to 3 significant figures, as shown on the screen there, 6.25 times 10 to the 5, or you could just write it as 6 times 10 to the 5. But of course you need to remember the units, and we're talking about the number of oxygen atoms that can fit across there. So the answer would be 6.25 times 10 to the 5, for example, oxygen atoms. And that's how we would do that question. So for the last question, we're asked how many nanoseconds there are in 1 year. And we're told to assume that there are 365.24 days in a year, to 5 significant figures. So we know that 1.0 times 10 to the negative 9 seconds is a nanosecond. And we're given how many days there are in a year in the question to 5SF. And because we're told just nanoseconds, and we don't necessarily need to assume a certain precision with that measurement, we can go to 5SF, because we would presume that that would be a least precise measurement. So, if there are a billion nanoseconds in a second, the initial part is not going to be 1.0 times 10 to the negative 9, but 1.0 times 10 to the 9, because for each second, like this one, there would be a billion nanoseconds in there. And we multiply that by 60 to get how many nanoseconds there are in a minute. Multiply this by 60 again to get how many nanoseconds there are per hour. Times by 24 to get how many are in a day. Times by 365.24 to get how many are in a year. And hence, to 5 significant figures, there are 3.1557 times 10 to the 16 nanoseconds in a year. So for the second half of this video, I just want to spend a little bit of time talking about scientific investigations and some key vocabulary associated with practical investigation methodology. So we'll start by looking at variables, which is something which can sometimes be somewhat confusing. However, if you have a clear definition and you understand the experiment you're doing, it should be easy to identify these variables. And over time, you'll obviously get more practice and you'll become better at doing this. But the independent variable is a variable that is deliberately being changed. So in science, we'll generally change something within an investigation to evaluate the effect of what that change has on some quantity. This quantity is a dependent variable, which is a measurement. Controlled variables are also very important. They're variables that we must keep constant in order to have a fair test. Let's say we were boiling water, for example, and we were boiling different volumes of water. And let's say that we used a slightly hotter temperature to boil one of these water flames. It would not be a fair test because we're simply looking at changing the volume of water and the effect that has on boiling time. If we were to increase the temperature as well, that would have another effect. So we wouldn't be able to determine what the effect of the volume has in isolation. So the independent variable for an investigation might be the concentration of hydrochloric acid. This would be for an investigation where you put a magnesium ribbon into hydrochloric acid and watch hydrogen gas being given off. So if we have the concentration of hydrochloric acid being different, then that's essentially the number of moles of hydrochloric acid we have within a solution. That could be something that we could change. And therefore, if we were to change that, a dependent variable could be the volume of hydrogen gas given off. We want to see if higher concentrations give off more hydrogen gas, or if lower concentrations give off more hydrogen gas. So the independent variable is what we're deliberately changing. We're deliberately getting out different concentrations of hydrochloric acid. And the dependent variable is the volume, because by having those different concentrations, we're probably going to have a different volume of hydrogen gas given off. And the controlled variables would be things like temperature. We'd have to keep the temperature constant while the chemical reaction is being done. Pressure would also be something. Time. It's unfair if we were to measure the amount of hydrogen gas, or the volume of hydrogen gas, after a longer period of time. And then also the size of the magnesium ribbon that we put in is important as well, along with the volume of hydrochloric acid that we have. That's just a little look at variables, and they're very important in designing a scientific investigation. With formulating a hypothesis, you're essentially making a prediction as to what would happen in the experiment, or what did happen in the experiment. Here's an example of a hypothesis on the board. It was predicted that as the concentration of hydrochloric acid increased, the volume of hydrogen gas would also increase. So, note that we're mentioning both the independent and dependent variable, and we're essentially explaining what we predict will be the effect of the independent variable on the dependent variable. When writing a scientific report after your findings, the entire thing must be in past tense. So your hypothesis should be in past tense when you are writing the paper, as you can see with the example hypothesis that I gave here. When you're actually planning the experiment, it's obviously going to be in future tense. You must remember to ensure that it is in past tense when you actually hand up the final paper, because it will be written after you've done the experiment. A method outlines the investigation and is essentially a procedure. So, when writing a method, you can do it in either dot point or paragraph form, depending on which is appropriate for the style of Prac report. However, it is always written in past tense. There should be clear instructions. These need to be so clear that one could actually reproduce the experiment that you did, without actually being there. So you're going to need to mention quantities, concentrations, everything like that. So for example, you might have to say 5 millilitres of 0.2 molar HCl, just so they're able to understand exactly what you did. And then make sure you specify all amounts and quantities, and ensure that you also mention replicates that you did. Because of course, you're not just going to have one sample and take one recording for a specific change in the independent variable. You're going to have to take multiple recordings. You're going to have replicates to ensure that you are getting an accurate set of results, not some complete random set of results. So by having replicates, you are averaging out the effects of random error. But I'll talk more about errors in just a moment after we've gone through results. The data table is very important for representing your findings from the investigation. As an example of a data table, there are quite a few key things I would like to point out. Units are not in each cell. Units are specified up the top. As you can see, we've got moles there and millilitres there. Significant figures are consistent down the columns. As you can see here, all these values are to two significant figures. The 0 in front of the decimal is not significant. Same with all the other columns. Significant figures are consistent. Thirdly, and very importantly, table values are centered. And this is really important. There are science teachers that will crucify you for not having these values centered. This is an important formatting technique. But our table is not complete yet. There is one last thing we need, and that is a relevant title and potentially also a caption. A title needs to be a clear representation of what the table shows. Generally, it will link to the independent and dependent variable again, and people can just read the table title and get an understanding of what they expect to see in the findings. So again, your title is critically important, and as is your caption, because you should be referring to this table throughout your discussion. As seen in Table 1, such and such, such and such, such and such. When you refer to your results, you're obviously producing a very good Prac report because you're understanding your findings and you're interpreting them. But that's what a data table should look like. Okay, so now on to the graph, and the graph is also a very important way to represent your data. Do not connect the dots between the points you plot from your data table. You should rule a trend line, which is indicative of the relationship between the two variables. Also, an important thing worth noting is that the independent variable is generally on the x-axis. Not always, but most of the time. Also, when you're drawing a trend line, do a nice smooth curve and only rule once. It's very important because if you do this, to try and get that curve there, it's not good at all. You need one smooth line. It may take you a couple of goes to get it, but one smooth line to show the data. Of course, you must label your axes. Hydrochloric acid concentration in moles. Remember units. Units are important. Volume of hydrogen gas in milliliters. I've also given my graph a title. Graph showing the effect of HCl concentration on volume of hydrogen gas produced. And you must have an appropriate scale to fit the data. As you can see, I'm going up here in 100 milliliter increments. I can't just go 100, 400, 500, 700 just to squish my data in there. That is not a good way to represent your data at all. Hydrochloric acid concentration across here, I'm going across in 0.1 of a mole each time. I'm not just going 0.1, 0.5, or whatever I just happened to test it. You need the scale. And show your points on the graph. It's very important that you show your original data points and then you rule a smooth curve through them. And those are the key tips for drawing a graph. There are other things as well. Sometimes you might need a legend because you might have multiple curves on the graph. But those are the key things when creating a graph. So for the discussion, you might explain the science behind what you have been investigating. So for example, you might have some balanced chemical equations or some diagrams. You might also want to comment on the reliability and validity of the investigation, the results and the method. So you might want to consider questions like, can the data be reproduced? Is it consistent with current scientific findings? And also, is the method a good way to collect data? Also make sure you link to and interpret what your findings actually mean in context of original aim or research question. So this brings us on to the idea of precision and accuracy, which is something very important to talk about with your results. So we've got a dartboard here, and we've got quite a few darts, and they're all grouped towards the center. Obviously that's high accuracy because we can see they're all near the center. It's also high precision because all of those darts are all near each other. They're all grouped up close together. This would be an ideal set of results because they're highly precise, there are not many outliers, and they're also very accurate. In some investigations, you might not necessarily know whether your results are accurate or not, but you can always talk about the precision or how far apart your data values are. So that's high accuracy, high precision. This one here is low accuracy and low precision. They're all on the outside, they're nowhere near the center, and they're all on this side, none on that side. So if we were to average them out, the average would probably be all the way over there. So they're not very precise because they're very spread out, and they're not very accurate either. With this data set, they're all spaced around, so it's actually quite low precision, but it's actually high accuracy, because if we were to take the average of them, it'd probably be in the center point there, because they're all equally spaced around. And what that actually means, this would generally be a fluke for something like this to happen, but it means that your experiment had a load of values all over the place, but if you average them, you get somewhere close to what the actual value is. So it's very rare that this happens, but still something interesting to consider. And the last one is high precision. They're all grouped together, but low accuracy, so they're all in the wrong place. And this generally symbolizes a systematic error, because it means that all your recordings are out by roughly the same value. We'll get into errors now. That's just a little look at precision and accuracy portrayed through dartboards. Lastly, I'd like to talk about errors. And there are two key types of errors that we look at when we're doing scientific investigations: systematic and random. Systematic are influenced by equipment or flaws in the methodology. It causes all recordings to be offset by a certain amount from the actual accurate result, as you saw with the dartboard example with the high precision, low accuracy. Random errors affect some recordings, influenced, they don't affect all recordings in the same way or by the same magnitude, but they are influenced by not controlling variables that should be controlled for a fair test in scientific inquiry. Generally, to reduce these, we control variables and we check the calibration of our equipment. However, after doing the experiment, you may come up with a few improvements to reduce the effects of these errors or to eliminate some of these errors. And you can always suggest improvements to the methodology in the practical report. So that pretty much covers everything I wanted to cover in this video. In the next video we'll start looking at the 4 fundamental forces, and we'll start moving away from all this science and maths preparatory work into the actual content of the nanotechnology course. So I look forward to seeing you then.